Hi everyone, in this video we'll be looking at the group 17 elements, otherwise known as the halogens. Do you know why this group of elements is known as the halogens? The HAL prefix actually means salt in Greek, while gen means to generate. So putting them together, halogen means to generate salts. So it tells us that this group of elements, they tend to form ionic compounds with similar properties with your metals. So group 17 elements are diatomic molecules. Do you still remember what's the meaning of diatomic? It means that there are two atoms chemically combined by sharing electrons. Recall in chemical bonding, group 17 elements, they have 7 valence electrons. So they need to share 1 electron in order to have a total of 8 electrons in the valence shell. Taking chlorine for example, if we were to draw the dot and cross diagram for chlorine, it will look something like this. I'm just going to show the valence electron. There is a single covalent bond between the two atoms. So structural formula can be represented like this. So diatomic because they share electrons and they exist as a molecule with two atoms joined together. So when we write the formula of fluorine, chlorine, bromine, iodine, you notice that it's always diatomic. Remember, nonmetals can not only just share electrons, they can also gain electrons. When they gain electrons, they form negative ions or anions, and the name of this group of anions are called the halides. Fluoride, chloride, bromide, iodide. They all have a -1 charge. Do not confuse between the term halogen and the halide. Halide refers to the negative ion. Okay, so it's quite common for students to mix this up and it means a world of difference when you talk about the atom or the molecule or the ion. So sodium chloride, sodium bromide, potassium iodide, these are the salts or what we call the halide salts. These salts are white solids and they dissolve in water to form colorless solutions. So your halide solutions, they are all colorless. So generally being non-metals, if you remember in chemical bonding, they have relatively low melting and boiling points. And the reason in terms of structure, why? Because simple molecular structure. So little energy is needed to overcome the weak intermolecular forces of attraction. They are also poor conductors of electricity. That is because they do not have any mobile ions or electrons. An interesting property of your halogens is that they are also colored, and we will look at the color in a while. Here's a table showing the properties of your group 17 elements. Can you identify some trends? Firstly, you will notice that the melting and boiling point increases down the group. The density also increases down the group. As a result of their increasing melting and boiling point, the physical state actually changes from gas to liquid to solid. There is also a trend in the color. Do you notice that they become darker as you go down the group? When you dissolve the halogen in water, they also form colored solutions for some of them. This refers to the aqueous solutions of your halogens. You need to know what the colors are as you will be required to describe observations. I have a periodic table app here. Let's take a look at your group 17 elements, starting with fluorine, a pale yellow gas. With many users, you will probably find fluorine in your fluoride toothpaste as the F- ion. Fluorine is also used to make polymers. One of the more famous one is Teflon, which is found in your non-stick pans. Chlorine is a greenish yellow gas, and like many halogens, they are rather harmful. In fact, during World War I, chlorine was used as a chemical weapon. You also find chlorine in bleach, which is a household chemical. Chemistry is interesting because the element itself, chlorine, is harmful, but yet when you convert it to the ion just by a change of 1 electron, gaining 1 electron, it becomes harmless. So sodium chloride as in table salt. Next we have bromine, which is a reddish brown liquid, and because of its low boiling point, it turns readily into a gas. Normally when you have a bromine sample, right, you will see it fuming because the bromine readily turns into a vapor. Next, we have iodine, which is a black solid but purple vapor. You will commonly find iodine in the pharmacy, which is used as a disinfectant for wounds. We don't do much chemistry with astatine because it is radioactive. Then finally, tennessine, which is one of the most recently discovered elements, which is also man-made. So given the trend in the table, can you predict what the properties of astatine might be? We see that the melting and boiling point increases down the group, so I would expect the melting point of astatine to be greater than 114. I also noticed the trend in physical state. Since iodine is a solid, astatine would be a solid as well. Finally, I noticed the color darkens down the group, so the color of astatine should also be black. Okay, so let's put the trends into words. What are some of the trends that we see described? So melting and boiling point increases down the group. Secondly, the color darkens down the group. And finally, the density increases down the group. Why does the melting and boiling point increase as we go down the group? This links to chemical bonding. They are all non-metals. We expect them to have a simple molecular structure. As you go down the group, the size of the molecules increases, and the strength of the intermolecular forces increases. As a result, you need more energy to overcome the stronger intermolecular forces of attraction. So the melting and boiling point increases. In the previous video, we said that group 17 elements, which are non-metals, they will gain electron when they react. This is unlike group 1 metals, which lose electrons when they react. So an element that is more likely to gain the electron is more reactive. So the trend in reactivity is actually opposite from that of group 1. So we have lithium, sodium, potassium. Then we have fluorine, chlorine, bromine. Potassium is the most reactive, while fluorine is the most reactive. So the reactivity increases down group 1, but decreases down group 17. So it'd be useful if you can do a bit of a compare and contrast between group 1 and group 17 elements in terms of their properties and reactions. So given that chlorine has more electron shells than fluorine, the valence shell is further away from the nucleus. Therefore, the electrostatic forces of attraction between the nucleus and the incoming electron is actually weaker. Because of that, there's less tendency to gain the electron. Therefore, the reactivity decreases going down the group. Let's talk about the chemical properties of your group 17 elements. Let's watch this video when chlorine water, which is a solution of chlorine dissolved in water, is added to aqueous potassium iodide. If you recall potassium iodide being a halide, the solution is colorless. Okay, and the solution of chlorine is also colorless. So refer to the table again for the respective colors. You notice that when chlorine is added, the colorless solution turns brown. Why does it turn brown? It is because iodine is being formed. And iodine itself has quite a low solubility in water. If there is a lot of iodine, you do notice some deposits of black solids at the bottom of the tube. Colorless solution turns brown. It's also possible to see some black solid form depending on the amount of iodine that you have produced. What do you think is going on? Okay, if you think about a chemical reaction between chlorine and potassium iodide, can you make a guess what is the product? So if we know that iodine is formed, we can sort of deduce that the other product is KCl. So let's balance the equation. Depending on the concentration of chlorine, it can go from colorless to a bit pale green or pale yellow. Okay, but generally you can just say it's colorless here. I want you to observe something. Do you notice that chlorine is kind of kicking iodine out of the equation? So now chlorine takes the place of iodine, correct? So this is what we call a displacement reaction. Chlorine displaces iodine from potassium iodide. So chlorine kicks him out to form iodine and potassium chloride. And this happens because of a difference in reactivity. Okay, so we can think about chlorine as being a more reactive element and iodine as a less reactive element. Think of a more reactive element as one that likes to find trouble. So we have chlorine coming over here, okay, and meets iodine, kicks him out of the equation, and then you have this. So that's what we call a displacement reaction. So the big idea here is that a more reactive element will displace a less reactive element from its compound. Try to fill in the blanks on this page and I'll go through the answers with you. Remember that your halogens are diatomic. I'll put in the state symbols as well. When you write on the equation here, we do not split the Cl2 because it's covalent. We only split if it's an ionic compound. Okay, so we keep this. We split this into 2K plus and 2Br minus. Likewise, we split this into 2K plus and 2Cl minus. Remember to apply the number 2 to both. So you can see that we can cancel the spectator ion and we are left with 2Br minus, 2Cl minus plus Br2. That's the ionic equation. Aqueous bromine is reddish brown. Solution turns from colorless to reddish brown. Take note of the template when it comes to answering questions like this. Compare the reactivity of the elements first. Then say element A displacing element B from whatever, okay, to form the products. Now you try again for the second one. Alright, you should have something like this. In terms of color, we start off with reddish brown, turns brown. Okay, the halides themselves solutions are colorless. Template, compare the reactivity of the elements. Displacement reactions are actually a type of redox reactions, so there is a link between these two topics. And because halogens, they gain electrons, it makes them strong oxidizing agents. We have reached the checkpoint. We can actually set up a matrix like this, a 3x3 table, to see what happens when we mix different combinations of halogens and their halide solutions. I will show you a video. Based on the observations you see in the video, fill in the table in your notes.
Here we are with a series of halogen halide ion displacement reactions. In the first 3 conical flasks here, we have potassium chloride. In the second 3 conical flask, we have potassium bromide. And in the third set of 3 conical flasks, we have potassium iodide. Into each of them, we're going to sequentially put iodine in this row, bromine water into this row, and chlorine water into this row. So let's have a look if any displacement reactions occur. Here's the iodine. You can see it stain the bottle deep brown colour. We're familiar with iodine. And if we place an approximate equal amount, a few mils, into each of those solutions, we see not much difference in the 3. Same colour for the iodine, and nothing appears to have happened. Into the second sequence of flasks, we're going to put bromine water. So this is quite nasty stuff. There's the bromine water. Quickly put the top back on the bottle. The bromine water, 0.02 molar. And let's introduce that into the 3 flasks. So we've got into the first flask, which is in bromine water in potassium chloride. This is bromine water into potassium bromide. And finally bromine water into potassium iodide. And hopefully you can see there that the bromine into potassium iodide has turned a much deeper orange colour than the other 2, perhaps indicating a difference in the reaction. Finally, we have chlorine water. Here's the chlorine water, and we're going to introduce that into the 3 flasks. So first, let's put some chlorine water into the potassium chloride. Then chlorine water into potassium bromide. And finally, chlorine water into potassium iodide. So once again, you can see a difference in the intensity of the colours there. The chlorine into potassium chloride, no noticeable change, but both into the chlorine into the potassium bromide, we've got a development of an orange-yellow colour, and into the potassium iodide, we've got that familiar iodine colour present there.
Okay, you can compare your observations to what you have here. Over here, I'm keeping the descriptions pretty short, just the final color. Okay. Alright, let's look at this question. We have chlorine gas, potassium bromide, potassium iodide. Okay, so when chlorine goes in to potassium bromide, what happens? Chlorine is more reactive than bromine. Chlorine displaces bromine. This will be reacted away, you form bromine. So at Q, you should have reddish brown vapor. And when the bromine gas further diffuses in here, it reacts with potassium iodide. Since bromine is more reactive than iodine, it displaces iodine from potassium iodide, forming iodine vapor. And after a while, as the iodine vapor cools, it deposits to form a black solid. So we see a purple vapor before the iodine deposits at the site as a black solid. Therefore, the correct answer here is C. Just now we talked about the template to answer questions on displacement. So when we have iodine, which is less reactive than chlorine, there is no reaction. That's because iodine is less reactive than chlorine. Iodine cannot displace chlorine from potassium chloride. We have come to the end of group 17 elements. Make sure you know their physical properties, the trends in their properties, and how to describe and explain displacement reactions. That's all for this video. I'll see you all in class.